Hi everyone, this is Mohammad Raza Ashuri, or you can call me Mo, and today I'm going to introduce you binary trees. So this data structure is one of the most data structure in computer science, okay? So have you ever wondered how your computer can compress a large file and reduces its size drastically without losing any of its content? Alright, so what is the answer? So the short answer is because your computer probably uses binary trees. So knowing the principle of binary trees allow us to better understand data structures in our course. So this is essentially important for the field of software engineering and programming. So this data structure is widely used in multiple programming languages, multiple popular languages such as Java, C++, C#, and so on. So in general, a binary tree or binary trees are used to store data in a searchable format. There are many real-world applications for binary trees. So I can give you some of those here. So first one is database systems. This database servers basically, or this type of systems uses binary tree for accessing data very fast and quickly, okay? And another application is sorting algorithms. For instance, in web search engines like Google, and so on. Behind the scene, they use this type of trees in order to access to web pages and content on that quickly. And even in system programming, for example, in the Linux kernel for process management and virtual memory manager and virtual memory system, we basically use binary trees or binary search trees. So binary searches, I'm going to basically touch them in the next few slides, are a form of the popular form of binary trees. Alright, so precisely a binary tree is a data structure that consists of nodes. So as you can see on this figure here, parent, right child, left child, and each node has at maximum, please pay attention, at maximum 2 children. So this simple structure allows us to easily perform number comparisons. Okay, so this is important for binary search trees. Okay, so this feature actually tell us when we want to add a node to our data structure, we want to add a new content or whatsoever. This, if for example our content are integers or numbers, so it will be compared to each node to decide whether it should be placed in the left or right side of the currently selected node. So don't get confused, don't be worried. I'm going to actually illustrate that with an online demo, okay? But now first listen to this. And in order to understand a binary tree, you can imagine like a family tree, okay? Like a family. And in family, there is such a relationships, and we have ancestors, right? Like grandmas or something, grandfathers. And we have descendants, right? Children. We have siblings, brothers, sisters, so on. So here in this tree, you can see this. I actually try to illustrate this relationship. So the ancestors nodes are further up in the tree, okay? They usually up, like root, the first one, grandma, grandpa, something, right? And the parents are always located above children, and children, or we call them descendants here, are located further down, all right? So here is an online demo to show you what do I mean by binary trees and binary search trees. So I use a free online tool which is called visualgo.net. So please go and surf this URL in your browser. But you can find a lot of alternatives. It's just for the sake of making a demo. So we create an empty basically tree. So here there is no any node, and then we say, okay, we want to add the first node. This is 95 because we have an integer, right? And then we are going to add some children to this node, okay? So we say 92, okay? So this is a smaller than 95 according to that principle, so it goes to left. And we want to add something a little bit bigger, with bigger number 90, let's say 99, okay? So 99 is bigger than 95, so it goes to right side. So now 95, which is a node, has two children. Okay, let's see, can we add another node and it goes as its children, or what happened? Because as I said, it must have at maximum two children. Okay, so if we add like okay, let's see, 96. Okay, 96 compared with 95, the root or ancestor here, or grandpa, whatsoever you can call it, and then compare with 99, and because it's smaller, goes to left. Okay, and now as you can see, 95 has at maximum two children, two direct children, and 96 here is a descendant, right? 99 and 92 are siblings, brother sister, brother brother, sister sister, and the parent is 95, but 95 is not the parent of 96, and it's essentially its ancestor, it's his grandfather. Okay, just imagine like this. Okay, now let's continue on our lecture today. Okay. So, the official definition for binary tree is an oriented tree such that each node has at most two children, a left and a right children. So, here is a larger example. A is the root. The other one, the green ones, are leaves, because these nodes have no children. That's why we call them leaves. And all the other nodes are called internal nodes. So there is one interesting point about binary trees when you compare them with organic natural trees. What's the point? Okay, interesting. So binary trees are oddly growing downward, and the root is located at top, right? It's A here. And leaves are located at bottom, okay? And here is top, bottom, okay? And this is basically in contrast to organic trees that grows basically upward, right? And this is like an agreement, like a protocol since 150 years ago. Okay, so the next important concept in trees or binary trees is the concept of depth. Okay, this is very important, particularly for this type of data structure. So the depth of a node, let's say node U, in a given binary tree, is the length of a unique path from root to U, okay, to that particular node. So essentially, node is equal to the number of edges in a path, and the depth of a root is 0, and node the same depth at the same level. So now let me illustrate this depth concept here. All right. So we want to know what is the depth of node with the number 96. So we search that. We say 96 and 1, 2, right? So the depth is the number of edges on a unique path from root to that particular node, which is 96 here. So the length, the depth of that is 2, 1, 2, okay? And the depth of the root node, here is 95, is 0. Why? Because there is no any edge for that. See, we didn't pass any edge. All right, so the depth for that is 0. Okay, and 99 and 92, which are basically siblings, they are on the same level. So we usually, in most of references, we start with level 0. Okay, in some references actually with 1, but we follow the consensus, accept that, and we say we start with level 0. So 95 level 0, the root always at the first level, which is level 0 here, and its children level 1. So these both, I mean, they are siblings too, are on the same level. And 96, which is there, is another level 0, 1, 2. So here you can see the depth, and so the depth of the root is 0, as I said always, and here its children, namely B and C, are at the depth 1, their children are at the depth 2, and so on. But the depth of the given tree, that's important to know. Another concept is the depth of the whole tree, and we define the depth of a given tree, which is, for example, tree T, is the maximum depth of any of its nodes. So what does it mean? So here it means the maximum depth here we have, they usually is in leaves, in leaves, right, in children. So the maximum here we have 4, and the maximum here belongs to R, which is located on level 5. Okay, and its depth actually is 5. 1, 2, 3, 4, 5. So the depth of the whole tree is equal to the maximum depth of its nodes. So the maximum node is 5. Therefore, the depth of the whole tree, tree T, for example, here is 5. So a single node tree has depth 0, because a single node tree means only root, only one node. An empty tree, it has depth -1, and this is just by convention, so we need to take it by granted. And in some cases we say we have full or complete binary tree, but what does it mean having a full or binary and complete binary tree? So let me actually illustrate this point. So this tree here is not complete. Why? What do you think? So think about it. Okay, so the answer is because each node here, in other words, basically in a complete binary tree, each node has to have exactly 2 children. Okay, that actually makes sense for 95, and here is right. Okay, it has exactly 2 nodes. But for 99, it has only one children. This is 96. And children in a complete tree doesn't need to have another one, so because they are leaves, okay, they are the end. Therefore, here is not complete because of the 99. 99 has no exactly 2 children, okay? And that's it. And also they are not on the same level. The level is not balanced here. So anyway, but if we add a few more nodes, let's say 90. And 93, it still is not complete and full balance. Okay, complete and full balance. So if we add 100, now we have a complete and full balance binary tree. This is perfect one. And this is important. Actually, in many operations, in the next lectures, I can actually explain you, there are many algorithms to basically balance a binary tree. But I will touch this point later on. So as I said, depth is an important concept here. So imagine we have a full and complete tree, like now is full because all of these nodes, internal nodes and ancestors, they exactly have 2 children. Okay. So, but please pay attention. There is actually a distinction between a full complete node with a balanced one. Okay, the balanced one has different meaning, but I'm not gonna touch that in this lecture. So a binary tree, so we suppose that we have a full and complete binary tree. That means each internal node has 2 children, okay? And on the level 0, which is the root level, we have only one node, i.e. the root. At the level 1 we have 2 power 1, 2 nodes. At level 2 we have 2 power 2, 4 nodes. At level 3 we have 2 power 3, 8 nodes. And continuing in this manner, the number of nodes at each level grows by the power of 2. Alright, so at the level at the depth d, we have 2 power d nodes. So we can say the total number of all these nodes can be described in a geometric series. Okay, and if we imagine the number of nodes in a given tree is equal to n, then this is equal to the sum of powers of 2 from 0 to d, which is the depth of the given binary tree, right? And this is finally equal to 2 power d, right, plus 1 and minus 1. So in a full complete binary tree, the depth is equal to logarithm n, okay, when n is the number of, is the total number of nodes. So this is very important and one of the reasons basically binary trees are very practical for various computer science challenges and applications is because of the cost of searching, scanning, insertion, retrieval, deletion, can be done in logarithm n, which is perfect and fast in comparison with other data structures such as linked list, and then we have linear order. Here you have logarithmic order, which is far more better, faster, especially when we deal with large scale data, such as big data that we deal with them in search engines. Okay. So, however, there is an issue here because the depth of binary trees are not always logarithmic. Okay. For instance, a binary tree may become unbalanced because of deleting different nodes and so on. So let me show you how it works. I will show you actually by demo. And when it becomes unbalanced, for instance, when each node, in a tree has at most one node, and then we have a skewed or degenerated binary tree, which basically turn this to a linked list. This is one example. This is actually a binary tree, which is true, but the performing various operations such as searching, deleting, adding, and so on would be in a linear time. So there is no any benefit of using that. So that's one of the important basically concept to balance a binary tree, right? Because this is part of nature. It happens by deleting information in some situation that could happen. So this is important. We perform algorithm for balancing binary trees. So let me show you this by a demo. So as you can see here, we have a complete binary tree and balanced binary tree. But how it could turn to a skew to an unbalanced tree. So if we remove here about, for example, let's see, 96, and if we remove like 92, just say, okay. So I want to make it simpler, so I remove the left side, and finally I remove 93. Okay. So now you see, because of this deleting information and maybe sometimes adding more information like this, we have a skew, unbalanced, unbalanced. Here we have an unbalanced skew, right skew binary tree, which is exactly like a linked list. So the order here is linear, is not logarithmic. Okay. So that was basically the lecture for today. You can, and these are the references I use, and for the visualization I use this online tool. I've also provided an assessment file for you, and that basically provides more details about binary trees. So please read that assessment carefully. And I also defined an exercise there. So I created a template class in Java for you, and I asked you please go and add multiple operations such as checking for the root, the size of the tree, the emptiness of that, and few simple operations. Please implement that and basically push and submit your code to your branch and the GitHub repository of the lecture. Thank you very much for your attention, and please ask your questions.